Welcome back. We were discussing the forming module of the course. So till the last class, we have discussed about different forming techniques, and we were discussing in detail about the extrusion processes. So starting with today's class, so as we have discussed about the extrusion process in the last class. So we have also introduced about extrusion constant K. So the extrusion constant is an overall factor that incorporates various variables such as flow stress of the material, frictional conditions at the die and container wall, and inhomogeneous deformation within the billet. So influence, the constant K plays a critical role in determining the total force required for extrusion, as it adjusts for these secondary effects that complicates the extrusion process. Now, what are the different types of deformation in extrusion? So so basically these deformation modes in case of extrusion depends on the frictional conditions prevails between the die and the billet getting extruded at their interface. So here you can see from this figure, so various characteristics deformation modes are discussed over here. So you can see. So here, this deformation process is influenced by factors such as container friction and lubrication, and of course, if there is proper lubrication of the die and the workpiece, the billet interface, then the frictional losses decreases and the deformation becomes easier. So in the case of nearly homogeneous deformation, that is figure A. So here. So the nearly homogeneous deformation occurs when the metal billet undergoes uniform deformation until it reaches the die entrance. So the conditions, so this deformation is typical in cases where there is low friction between the billet and the container wall. That means the billet is well lubricated. The billet die interface is well lubricated. Hydrostatic extrusion technique is used where the billet is surrounded by pressurizing fluid or liquid, and indirect extrusion is performed. As we have discussed in the earlier classes, that you need lesser pressure force, extrusion pressure in case of indirect extrusion, because in case of indirect extrusion, as we have discussed earlier, that there is no friction at the workpiece billet and the container wall interface, because in case of indirect extrusion it is the pressurizing ram that moves. However, the billet the workpiece which is undergoing extrusion remains stationary. So that is why the pressure requirement in case of indirect extrusion is much lesser than we observe in case of direct extrusion. So typically the homogeneous, near homogeneous deformation can be a characteristic feature of indirect extrusion. So the effect of nearly homogeneous deformation is the deformation is uniform, which means less energy is wasted to counter for the friction or non-uniform deformation pattern. So now the next case, that is increased container wall friction. So that means this is a case where the container and the billet interface is not well lubricated. So then the frictional losses are more. So as the friction between the container wall and the workpiece billet increases, the deformation pattern changes, leading to severe distortion of the grid pattern in the corners of the billet. So as observed in case of figure B. So this is a case of where increased container wall friction is showing up. So you can see the distortion towards the wall, at the just beside the entry of the workpiece billet into the die. So you can see that it also causes a dead zone formation, which is marked over here with these circles. So this distortion results in the formation of dead zone where the metal becomes stagnant and undergoes minimal deformation. Okay, so as you can see from this deformation of these grids, that the material is flowing from the center of the workpiece to bottom, to achieve the shape of the extruded billet. However, the metal which is remaining at the corners of the container wall, it does not undergo the deformation at all, and hence it facilitates the formation of dead zone. So the deformation types, so center of billets, grid elements at the center of the billet undergo pure elongation stretching into the extruded rod, and near sides, grid elements near the sides of the billet undergo significant shear deformation. So, due to friction and distortion, and so this is the case of increased container wall friction. And now when we are moving to the third case, that means high friction at container billet interface. So, when the friction becomes even severe, so then you can see the amount of dead zone formation is even higher. So, in this case you can see that there is a strain gradient formed within the workpiece material, and that leads to inhomogeneous deformation of the workpiece material, leading to the formation development of the extruded billet. So, when high friction exists between the billet and the container wall, the metal flow is concentrated toward the center of the billet, leading to an internal shear plane developing towards the center of the billet. So, then the surface chilling. So, this condition can occur if the surface of the billet is chilled by a cold container, making it more resistant to deformation along the side. So, what is the so the internal shear plane causes the center of the billet to deform more than the edges. So, there is a deformation gradient at what I told you at the beginning. So, so that concentric deformation away from the container wall. So, that is why the dead zones are forming. So, this is the characteristic feature when we are talking about the case extrusion scenario where there is high friction at container billet interface due to lesser lubrication. So, which leads to inhomogeneous deformation. And now, so the case when sticking friction and shear zone formation. So, sticking friction, as we have discussed in case of earlier rolling also. So, then sticking friction generally exists at the in case of extrusion between the billet the workpiece billet and the container wall, and the metal separates internally along a shear zone. So, you can understand from this schematic again, and also you can understand from this image as well. So, then because of this sticking friction at the wall, so what happens that there is a thin skin that remains within the container, because the because of higher friction the metal does not move at all at the metal which is at the interface between the workpiece and the container wall. So, it becomes stationary, hence it becomes so the metal, because of the extrusion pressure, it leaves a thin skin behind which is attached with the container wall, and it gets extruded and then so that is the beneficial aspect of this thing is that the extruded billet which comes out which comes out from the sticking friction region. So, then the oxide scales which are otherwise present in the workpiece billet which is being extruded. So, the thin skin contains those oxide rich regions and the defects, and the extruded billet comes out to be clean and defect free. So, the surface of the extruded product consists entirely of clean raw new material, as the older surface layer is left behind in the container. So, these are basically the different kind of deformation modes that we observe in case of extrusion processes. So, now, if we talk about the plastic work of deformation that is involved in case of extrusion process, which is termed here as UP is equal to sigma 0 prime, which is the effective flow stress into ln AF by A0, that is the final cross sectional area divided by the initial cross sectional area. So, as we know that area reduction ratio R is equal to A0 minus AF by A0. So, that means is equal to 1 minus AF by A0. Okay. So, that means AF by A0 is equal to 1 minus small r, that is the area reduction ratio. So this is the area reduction ratio. So, here but here we are introducing capital R, which is called the extrusion ratio. So, which is the area so here so the extrusion ratio is basically initial area, that is A0 divided by AF. Okay. So, then so the work involved in case of in case of extrusion, W is UPV, that is plastic work of deformation multiplied by the volume of the extruded material. So, then the expression becomes, so if you put the expression for UP over here, so the resultant expression become V into sigma bar, that is effective flow stress ln capital R. So, what is capital R? It is the area reduction ratio in case of extrusion. extrusion. So, here area, because R is equal to A is 0 by AF, that is initial area by final area. So, but here we are getting the expression of UP as sigma prime ln AF, that is final area by A0. So, then if you just change it in the form of from here to so then minus sigma bar ln A0 by AF. So, that you can express it in terms of the area reduction ratio in case of extrusion. So, then sigma bar ln R. So, this is the expression for UP. So, so this minus sign we are basically neglecting, and then finally, we are calculating the work involved by multiplying with the volume of the extruded metal, and the resultant expression becomes V sigma bar ln R, which is equal to P into area into length. Okay. So, here P is the extrusion pressure and A I L are the cross sectional area and length of the extruded billet. So, the extrusion pressure is becoming equal to P is equal to sigma bar ln R. Okay. So, here volume is equal to area into length. So, that is why P is equal to sigma bar ln R. So, this is a idealized expression for the extrusion pressure, which is neglecting friction and redundant deformation. We will see in the latter in the course that how we can consider the effect of friction and redundant deformation, and how we can modify the extrusion pressure or drawing pressure later on. So, the efficiency. So, the eta is the process efficiency ratio of ideal to actual energy input energy per unit volume. So, the actual extrusion pressure, so P E is equal to P by eta. So, that means so because we need to divide it by the process efficiency. So, that is why P by eta, that means sigma prime sigma bar ln R by eta. So, this is the analysis of extrusion pressure is crucial for direct extrusion processes. It is also crucial for indirect extrusion processes, and the efficiency influences the actual pressure affecting optimization. So, so now moving ahead. So, the total extrusion force P E basically is the sum of die force, that is P D, the force required to push the billet through the die, and the frictional force, that is P F, that is the friction force between the container liner and the billet, that means which is present at the container and the billet interface. So, assume that this is the container. So, this is the workpiece billet which is present within the container, and then this is the die. So, this is the where from the extruded billet is coming out. Okay. So, this is the so the force present at the die, so that is P D, and the force present due to the frictional force, friction exists between the the container wall, container liner, and the workpiece material. So, here this is the frictional force, that is P F. So, and P F can be divided into two sub parts, that is P F B, that is the friction between the container liner and the upset billet, and P F F, that is friction between the container liner and the follower. However, frictional force between the container liner and the follower is generally considered negligible. So, it is approximated as 0. Hence, the extrusion force formula P E can be expressed as P D plus P F B. So, P D plus P F B, that means that is the die force plus the frictional force between the container liner and the offset billet. Okay. So, the frictional stress assumption. So, the frictional stress can be defined as tau I, because it is a shear stress. So, it is assumed that the frictional stress at the interface between the billet and the container liner is nearly equal to a constant. So, tau I equivalent to K. So, then so here, so ram pressure due to container friction, we can express the extrusion pressure P E is equal to P D plus P F, or P E is equal to P D plus P F B, as we have discussed in the previous slide. So, this is the expression for the extrusion pressure. So, then which is equal to P D plus 4 tau I and the length of the billet divided by D. Here, so how we are arriving the this expression for the this frictional pressure between the container liner and the billet. So, then so if we have to calculate the friction force, so then we have to multiply the pressure generated due to friction between the container liner and the billet with the the area, cross sectional area. So, pi by 4 d square. So, which is equal to the shear stress into the surface area, that is 2 pi r L, that means pi d into L. So, then how we can calculate the expression for P f or P f b? So, P f is taken equal to P f b, because the as we have discussed earlier that the friction between the billet and the follower is neglected, which is negligible to 0. So, then here it becomes tau I into pi d L into 4 divided by pi d square. So, pi gets cancelled, d becomes so then it becomes tau I L 4 by d. So, this is the resultant expression, that is 4 L tau I by d. So, that is the expression for P f b. So, then it constitutes as a whole the expression for the extrusion pressure. So, that is P e. So, here d is the inside diameter of the container liner and tau I is the uniform interface shear stress between the billet and the container liner, and L is the length of the billet in the container liner. So, this shows that the ram pressure required due to container friction depends on the diameter, length of the billet and the interface shear stress. So, the total extrusion force P e can be expressed like this as written above. So, it is just repeated again over here. So, this L is not the subscript. So, please correct it. So, this is so this is the expression. So, it is same from here. So, this equation shows that the total extrusion force is a function of the die force, billet length, diameter of the container and the interface shear stress between the billet and the container. So, determining frictional shear stress. So, by measuring the total extrusion force P e and the die force P d, it is possible to determine the frictional shear stress. This can be calculated as, so from this expression you can quite very easily calculate this. So, then from here so it is basically P e minus P d, that is total extrusion pressure minus extrusion pressure due to the die friction and then is equal to 4 tau I into L by d. So, that means tau I is equal to d into P e minus P d by 4 L. So, this is the expression which can be utilized to calculate the shear stress, frictional shear stress that is generated between the container liner and the workpiece which is undergoing the extrusion. So, this is the expression for the frictional shear stress. So, this enables a precise understanding of how friction affects the total extrusion force and provides insight into the performance of the extrusion process. So, the summary here is the total extrusion force consists of the die force and the frictional force, and the frictional forces are influenced by the length of the billet, diameter of the container and the uniform interface shear stress. So, the equation P is equal to P d plus 4 tau I L. So, again this is not a subscript. So, by d. So, this highlights how friction and billet properties impact the total force required for extrusion process. So, now die pressure P d and slab analysis. So, the slab analysis is a simple approach to determine die pressure P d which involves using slab analysis to account for friction when extruding through a conical die. So, Coulomb sliding friction. So, this analysis uses Coulomb sliding friction principles to estimate the die pressure. So, relation to wire drawing. So, the solution for the extrusion die pressure is analogous to wire drawing through a conical die and can be expressed as P d is equal to sigma x b is equal to sigma 0 1 plus b by b into 1 minus r to the power b. So, where sigma x b and sigma 0 are the stresses, b is equal to mu cot alpha into so where b is a function of the coefficient of friction mu. So, neglect this. So, mu and the die semi angle or semi die angle alpha, and where r is equal to a0 by a, that is the extrusion ratio, that is initial cross sectional area divided by the final cross sectional area. So, a0 by a or a0 by af as you can understand. So, this is the expression for the this die pressure or in case of extrusion, and also it is analogous to the wire drawing process. So, then here let us define the key variable. So, here B is defined as mu cot alpha, where mu is the coefficient of friction, alpha is the semi die angle, that is the angle of the die at the conical portion where extrusion takes place. So, I mean so basically it is the this angle here is talked about. Okay. So, this is the billet which is undergoing and the wire drawing process, and then the resultant billet is forming. So, this is the workpiece billet, and this is the alpha angle, semi die angle or angle of attack, or the whatever I mean. So, the various names it can be called about. So, R is the extrusion ratio defined as initial area by final area. So, A0 by AF. So, where A0 is the initial cross sectional area of the workpiece and AF is the final cross sectional area after extrusion or wire drawing. So, consideration of die friction. So, die friction only. So, this analysis accounts only for the die friction, but does not consider redundant deformation. So, which refers to so earlier we have defined the expression for the total extrusion pressure without considering die friction and redundant deformation. So, now we are considering die friction, but still neglecting the redundant deformation. So, that means it refers to energy expended on internal shear deformation that does not contribute to useful metal flow. So, then importance of friction. Friction is critical in determining the die pressure as it directly influences the force required to extrude the material. So, extrusion problems and slip line field theory. So, the most studied problems. So, extrusion is one of the most studied problems in metal forming and is often analyzed using slip line field theory. So, the plane strain deformation. So, in this analysis the problem has been studied for plane strain deformation, where deformation occurs in a specific plane without considering the effects of friction. So, the general solution for die pressure. So, the simplified solution, a general solution for die pressure which does not include friction can be expressed as PD is equal to sigma 0 into A plus B ln r, where A and B are constants typically used for specific extrusion cases. For axisymmetric extrusion, typical values of these constants A and B are 0.8 and 1.5 respectively. So, this formula provides a way to calculate the die pressure without explicitly accounting for friction, but based on the natural logarithm of the extrusion ratio. So, here extrusion ratio capital R, as we have already defined, is equal to initial area by final area. So, this is the extrusion ratio R. Okay. So then moving ahead. So, as per Kudo's upper bound analysis. So, Kudo provided a formula for extrusion through rough square dies, where 2 alpha is equal to 180 degree. So, the die pressure PD can be expressed in that case as sigma 0 into 1.06 plus 1.55 ln r. So, it is coming from this expression, where we have incorporated the values for A and B. Okay. So, where R is the extrusion ratio and sigma 0 is the flow stress of the material. And now, so Abhidzur's generalized expression. So, Abhidzur extended the analysis for lubricated extrusion through a die of semi angle alpha. So, it is please correct this. Okay, alpha, incorporating a spherical velocity field. So, the equation for die pressure PD in line with Abhidzur's generalized expression becomes like this, which is PD is equal to 2 sigma 0 by root 3 into alpha by sin square alpha minus cot alpha plus sigma 0, that is the flow stress, into 2 function of alpha plus m cot alpha into ln r0 by rf plus 2m bracket L by r0 minus 1 minus rf by r0 into cot alpha, where m is the interfacial friction factor and f alpha is a complex function of the semi die angle alpha. Okay. So, it is alpha, and r0 and rf are the initial and final radii of the billet respectively, and L is the length of the die land exit region of the die, r0 radius of the billet before extrusion, rf radius of the extruded product, and f alpha for small die angles, f alpha approaches 1. So, this is the generalized expression given by Abhidzur to calculate the die force in case of extrusion. Okay. So, upper bound analysis for die pressure. So, a recent upper bound analysis using a different velocity field aligns well with experimental results for hydrostatic extrusion. So, DPRA use the following equation to describe die pressure as PD is equal to sigma 0 A plus B ln r plus mk cot alpha ln r. So, you just try to see this. So, here I mean as per upper bound analysis, this part is added, compared to the this general solution for die pressure. This is the difference from the simplified solution for die pressure, which states only as sigma 0 into A plus B ln r. So, there is no frictional terms here. However, in case of here, so here so the interfacial shear stress is considered. So, the effect of friction is considered in case of upper bound analysis, and accordingly this term is introduced where this mk cot alpha ln r is added, where m is equal to tau I by k. Okay. So, the ratio of the interface shear stress to flow stress. So, A and B are constants dependent on the semi die angle alpha. So, values of constants A and B. So, these are some typical empirical values for A and B. So, where the semi die angle alpha is 30 degree, then A and B assumes the value of 0.419, 1.000006, and simultaneously it changes this constants changes their value when the semi die angle increases to 45 degree and 60 degree. Okay. So, you need not to keep these values in your mind. So, if there is problem asked, then these values will be provided. However, it is good to know. So, the variation of the constants value with the increase or the change of semi die angle. So, now let us discuss about the flow distribution in case of extrusion. So, the flow distribution during extrusion was measured using billets gridded along the diametral plane. So, the technique of viscoelasticity allows detailed mapping of the strain and strain rate distribution, as well as the calculation of temperature and flow stress variations within the extrusion process. So, the local strain rate variations, the figure it is given in the next slide. It shows local maxima and strain rate near the die exit and along the surface and central line of the extrusion. So, this highlights the complexity of flow distribution within the billet. So, now let us we have discussed about the mechanics involved in the extrusion process, and we also have discussed about how to calculate the die pressure, how to calculate the overall extrusion pressure when die pressure and along with the frictional pressure that is exists between the container liner and the workpiece material interface. So, we have discussed how to calculate that. So, now let us discuss about the overview of the hot and cold extrusion techniques. So, as the name implies, so cold extrusion involves cold forming of small machine parts such as shafts, pins and cylinders from rod and bar stock. Other processes like upsetting, expanding and coining are also considered cold forming. So, axisymmetric parts are specially suited for this process due to high production rate, precise dimensional control and good surface finish. So, this hot extrusion and cold extrusion is analogous to hot and cold rolling that we have discussed earlier in this module. So, so generally the cold extrusion is of course happens below the recrystallization temperature, whereas the hot extrusion happens above the recrystallization temperature. So, as the advantages of cold extrusion is also quite similar that we have discussed in case of cold rolling. So, the advantages are that it in cold extrusion induces strain hardening, allowing the use of cheaper low alloy materials. So, this makes cold formed low alloy steels widely used in the automotive industry. So, the strength properties that can be achieved is higher in case of cold extrusion that it can be achieved in case of hot extrusion. However, the deformation is much easier in case of hot extrusion. So, then it is the choice that need to be made as per the industrial requirement and the problem in hand, that whether to opt for cold or hot extrusion technique. Okay. So, yeah. So, then moving ahead, the limitations and extrusion ratios. So, hydrostatic extrusion has practical limitations with a fluid pressure cap of 1.7 GPa. So, this limits the extrusion ratio for materials like mild steel to less than 20:1. So, but for softer materials like aluminum, ratios over 200:1 are achievable. So, this is huge. So, you can understand that it is 200 times reduction of cross sectional area can be achieved, and analogous increase in the billet length can be achieved in case of softer metals, which is not the case due to the higher requirement of total extrusion pressure in case of materials like steel, which are difficult to extrude compared to softer materials. And tubing production via extrusion. So, hollow tubes, like if you can recall, we have discussed during casting module that we generally use centrifugal casting technique for developing hollow pipes. However, based on the structural integrity on demand of these hollow tubings can also be produced by extrusion route. So, with close tolerances through extrusion by attaching a mandrel to the extrusion ram. So, the mandrel controls the wall thickness, and a hollow billet is typically produced. So, typically used for this purpose. So, to ensure concentric tubing, the ram and mandrel must be in perfect axial alignment with the die and the container. Okay. So, so now porthole die extrusion. So, a method used for aluminum and magnesium based light alloys, where a solid billet is extruded through a porthole die without a mandrel. So, metal flows around a central bridge and joins in a welding chamber. So, forming a seamless tube. Porthole extrusion is commonly used for a hollow unsymmetrical shapes in aluminum alloys. And seamless versus welded tubing. So, tubing can be classified as either seamless or welded. Welded tubing is formed by welding a strip, while seamless tubing is produced by methods like extrusion. So, particularly for metals that are difficult to work with. So, then Mannesmann mill. So, it is used for rotary piercing of steel and copper billets. So, the process creates a tube cavity by applying axial thrust and tensile stress, which opens the billet center around a piercing point, and it is one of the most severe hot working operation for metal. So, you can understand it is basically twofold. So, there is a piercing happening to get the hollow section, and then from the top there is a tool which is trying to reduce the thickness. So, there is two-way deformation happens simultaneously to a workpiece to achieve this hollow pipe shape. So, that is called as a Mannesmann mill. So, this is a so you can understand that it is a very high and severe plastic deformation process. So, so this is the case of plug rolling and piercing. So, plug rolling mills elongate the pierced billet using a long mandrel and plug. So, the elongator with three conical rolls improves the tube concentricity and surface finish. So, final steps involve reeling to burnish the tube's inner and outer surfaces and correct any ovality. So, this is also quite similar to the schematic that I have drawn in case of Mannesmann mill. So, here also the target is to get hollow tubings with desired inner and outer desired surface finish in the inner and outer surfaces. And then the drawing operations. So, in drawing operations, metal is pulled through a die via tensile force with most plastic flow caused by compression. So, we will discuss about the drawing operation in the next class. However, we will summarize in case of in the present class that so whenever we are trying to develop hollow pipes through extrusion technique, it generally involves a severe deformation to the workpiece billet to achieve the desired shape, and it can only be applied to metals which are capable of withstanding that much deformation without undergoing premature failure. So, with this I am done for the class, and we will meet with in the next class with the wet drawing process. Thank you.